Orders are failing. Grafana is spiking to 50%. It's 3 a.m. and you have no idea which service broke. What if you could find the root cause in under 30 seconds? That's what observable systems do. Let's build one. Before we look at any code, let me give you one analogy that explains the entire project. Think of it as a restaurant. Your code is the kitchen. Docker is the building that houses it. Kubernetes is the franchise manager who makes sure every kitchen section always has enough cooks. The load balancer is the main entrance, the first thing every customer hits. NGINX is the host inside who directs you to the right table. Terraform is the architect who designed the building. GitHub Actions is the delivery driver who brings updates. And Prometheus and Grafana, that's the health inspector and the dashboard on the wall. Every tool has a job. Keep this picture in your head. It makes everything else click. First concept, microservices. Why split one app into 4? Imagine a restaurant where one person does everything: cooking, taking orders, handling payments, and making deliveries. If that person gets sick, the whole restaurant closes. That's a monolith. Now split it. One chef, one cashier, one waiter, one delivery driver. If the delivery driver is sick, food still gets cooked and orders still get taken. That's microservices. In this project, each service has its own database, its own container, and can be deployed independently. Fix order service without touching user service. Now the tools, each one explained in one analogy. Docker. Before shipping containers, loading a ship was chaos. Every item needed different handling. Shipping containers standardized everything. Same box, any ship, any crane. Docker does that for software. Package your code once, run it identically everywhere. Kubernetes, the franchise manager. You tell it, I want 2 copies of order service always running. It makes sure they run, restarts them if they crash, and scales up during the lunch rush. Terraform, the architect's blueprint. Instead of clicking around in the AWS console, which is slow and not repeatable, you write exactly what you want in code, and Terraform builds it. GitHub Actions, the robot assistant. You push code. The robot builds the image, pushes it to ECR, and deploys it to Kubernetes. You never touch a server manually. Prometheus and Grafana. The health inspector visits every service every 15 seconds and records the numbers. Grafana turns those numbers into the speedometer on your dashboard. VPC, your own private floor in a shared AWS office building. Other tenants are on different floors and cannot walk in. Public and private subnets. The reception desk faces the street. That's public. The back office has no walk-ins. That's private. EKS nodes live in the back office. NAT Gateway. The receptionist who fetches things from the internet for the back office, but never lets outsiders in directly. Load balancer. The building's main entrance with a security guard who directs every visitor to the right service. IAM, ID badges. GitHub Actions gets a badge that opens only the ECR room and the EKS read-only room. Nothing else. Now you know the concepts. Here's what we're actually building, not a tutorial app. A production-grade food delivery platform. 4 FastAPI services, Terraform VPC and EKS, GitHub Actions CI/CD, HPA autoscaling, and a full Prometheus Grafana stack. It costs about 19 cents an hour on AWS. $0 after Terraform destroy. Here's the full architecture. A request comes in through an AWS network load balancer. That's your single entry point. NGINX ingress controller sits behind it and routes traffic to one of 4 services: user, restaurant, order, or delivery. Each service runs in a private subnet, no direct internet access. They talk to their own SQLite databases, no shared state between services. Order service makes one synchronous call to restaurant service to validate items, with a 5-second timeout. Prometheus scrapes metrics from every service every 15 seconds and feeds Grafana. Everything runs on 2 T3 small EKS nodes managed by Kubernetes. Terraform provisions all of this: VPC, subnets, NAT Gateway, EKS cluster, node group, ECR repos, and IAM roles. in a single apply. Here's every tool in the stack. FastAPI, async Python. One line gives you a metrics endpoint. Docker, multi-stage builds, non-root user. Terraform, 4 modules, 47 AWS resources. AWS EKS, Kubernetes 1.29, HPA, manage control plane. GitHub Actions, matrix strategy, 5 services build and deploy in parallel on every push. Prometheus and Grafana, pre-built dashboard, catches failures in 30 seconds. Let's build this from scratch on AWS. Live on screen. 4 Terraform modules. We'll walk each one. VPC first, the network everything runs on. CIDR 10.0.0.0/16. 2 public subnets, 2 private subnets, spread across 2 availability zones. Public subnets have map public IP on launch true, that's where the load balancer lives. Private subnets have no such line, which means it defaults to false. Nodes get no public IP, unreachable from the internet directly. Every request must come through the load balancer. NAT Gateway in the public subnet, outbound-only proxy for the private nodes. They pull Docker images from ECR through it. No inbound connection can start from outside. 1 NAT across 2 AZs is a cost trade-off, 4.5 cents an hour. Documented right in the code. EKS module, the Kubernetes cluster. 2 IAM roles, node group, launch template. 2 IAM roles, not 1. Cluster role, assumed by the EKS control plane running in AWS's account. It calls EC2 and ELB APIs on your behalf, creates load balances, registers nodes. Node role, assumed by your EC2 instances. They pull from ECR and register with the cluster. Separate trust boundaries. Neither can assume the other's role. Critical policy on the node role. Amazon EKS CNI policy. The CNI plugin assigns VPC IPs directly to pods. Without it, pods start, show running, but have no IP. Can't talk to each other. Can't reach the internet. Everything looks fine until you use it. Number 1 EKS setup mistake. Node group uses the private subnet IDs from the VPC module output. This is how modules connect. VPC outputs subnet IDs, EKS consumes them. ECR module, 5 repositories, 1 per service. User service, restaurant service, order service, delivery service, frontend. Created by Terraform. Used by GitHub Actions to push and pull images. Last module, IAM for GitHub Actions. Least privilege. ECR push-pull and EKS describe only. Cannot create or delete AWS resources. Cannot touch IAM. If these credentials leak, and CI credentials do leak, blast radius is contained to the pipeline. Cluster up. Food delivery dev. Kubernetes 1.32. The managed node group is active with T3.small worker nodes. EC2 worker nodes are named from the launch template. They are running in private subnets and have no public IP. That means the nodes are not directly reachable from the internet. 5 ECR repositories are ready. They are empty before deployment. GitHub Actions pushes the first images here in the next section. 1 file does the entire deploy. 2 jobs set up cluster and build and deploy. A push to main triggers it automatically, and workflow dispatch lets us run the exact same deployment manually from GitHub Actions without making a dummy commit. Setup cluster runs first. Applies all Kubernetes manifests namespace, deployments, services, HPA, ingress. Then installs Prometheus stack via Helm. This job ensures the cluster state is correct before images are pushed. Build and deploy uses matrix strategy 1 runner per service. All 5 run in parallel. Fail fast false means one failure doesn't cancel the others. Each job is fully independent. Image tag with a get SHA, every image traceable to an exact commit. Bad deploy goes out, you know exactly which commit to revert. After kubectl set image. Job blocks on rollout status 5-minute timeout. Kubernetes must confirm new pods running and old pods terminated before the job completes. Rollout hangs bad image. Failed readiness probe job fails. GitHub alerts you. For the demo, I'm running it manually. In day-to-day development, the same workflow also runs automatically when code is pushed to main. Setup cluster runs first, manifests applied. Then 5 parallel jobs kick off. Watch them run simultaneously. ECR login, Docker build, push, kubectl set image, waiting on rollout. All 5 independent. All 5 workloads are running in the food delivery namespace. Each service is 2 replicas. GitHub Actions built the images, pushed them to ECR, updated the Kubernetes deployments, and waited for each rollout to finish. ECR now has real images from the workflow, each tagged with the commit SHA and latest. Kubernetes has deployments, pods, services, HPAs, and ingress manifests applied. That completes the production deployment path. Terraform infrastructure, GitHub Actions CI/CD, ECR images, and Kubernetes workloads running on EKS. This is not localhost and not Docker Compose. This URL is the AWS load balancer created by the Ingress NGINX controller. The browser hits the load balancer. Ingress routes traffic to the frontend and API services, and the order flow runs across the deployed microservices inside EKS. The deploy workflow also installs Grafana with a public load balancer for the demo. This gives us the operational view, cluster workloads, service metrics, and dashboards from the same EKS environment where the app is running. After sending traffic through the real EKS load balancer, Grafana starts showing request rate, latency, and order metrics from Prometheus. We're not doing the failure demo in this walkthrough, so error panels should stay quiet. This is the final state. Deployments created, pods running, services and ingress applied, HPAs attached, an external load balancer serving the real app, and Grafana exposed for dashboard verification. You went from nothing to a working EKS deployment path in one video. Infrastructure as code, automated container builds, ECR image storage, Kubernetes rollout, browser verification, dashboards, and repeatable cleanup. 7 production skills in one project. IAM roles, the 2-role EKS model and the CNI footgun. VPC design, private nodes and NAT for outbound access. CI/CD, 5 services build and deploy in parallel. HPA, autoscaling policy attached per service. Inter-service timeouts, one slow dependency should not take down the system. Rolling updates, Kubernetes waits for healthy pods. ECR traceability, every image maps back to a commit. These are the mechanics behind a real production deployment. Most important command of the video. Terraform destroy. Every resource you created, EKS cluster, node group, NAT gateway, load balancer, ECR repos, IAM roles, gone. 37 resources, back to 0. The NAT gateway alone costs 4.5 cents an hour. The EKS control plane costs 10 cents an hour. Leave this running for a week and you've spent real money. Always destroy after recording. Infrastructure as code means you can rebuild it in 15 minutes whenever you need it. Full repo in the description. README has the architecture diagram, cost breakdown, every API endpoint, and the full deploy guide. Drop a comment if you get stuck. I read every one. Subscribe for Project 2. See you there.